Okay, so last time we were talking about distributed snapshots. If you remember, we looked at the problem of how to essentially save the state of a distributed system, so that if any process crashes in that distributed system or application, you can terminate all of these processes that constitute part of the system, load the saved state, the most recent saved state, which is called a snapshot, and then restart from that point on. So that's when we talked about how do you take these snapshots without assuming that there is a synchronization algorithm or a physical clock or any of that sort. So we are going to continue from that point on. I'll talk briefly about the problem of termination detection, which comes from the problem of distributed snapshots. So we are just going to use that and figure out how to solve this problem. Okay. And then for much of the class, we are going to talk about leader election and mutual exclusion. Okay. And so these are, so mutual exclusion is how do you do a distributed lock. Okay. How do you lock, implement a lock when you have a distributed system. And then leader election just says how do you pick a coordinator process or a master process dynamically. Okay. So that's what we are going to do today. So let me start with the problem of termination detection. Okay. So what is the problem first? So termination detection simply means whether the distributed computation that you have or a distributed system that you have implemented and is running has finished, and you can essentially shut down the system. Okay. So you might have a distributed simulations, let's say. So set of jobs that are processes that are running on multiple machines that are performing some simulation. How do you know that the program has ended? Okay. If you have a centralized application, the program ends, it just terminates and essentially it's done. Okay. In a distributed system, you cannot actually shut down one process until you know other processes are done, because they might send you a message that require you to do more work. Okay. Just because your local work is done doesn't mean that the work in the system is done, because there's communication, and when messages arrive or RPC messages are sent, you might do more computation. Okay. So you can only say that the system as a whole or your distributed application is done when everyone is done, not just one process is done locally. Okay. The question is, how are you going to figure out that everyone is done? Yeah, the answer is not that complicated. You got to ask everyone. If everyone says they're done, then you're done. Okay. That's the point. But there's an algorithm to do this, and you can just piggyback this on top of the distributed snapshot algorithm. Okay. Since you already know how to do distributed snapshot, you can say as part of taking the snapshot, let's also query every process and ask them whether they finished their computation. If every process in the system says that they have all finished, there's no more work to be done, then we know that everyone has finished, so all of them can terminate. But if any process says they are still computing, there are some messages that they are processing, or there's some other computation to be done, then you got to say that we got to wait, because that computation may trigger more messages, that those messages may go to other processes, they may trigger more messages, so everyone might still have quite a bit of work remaining to be done. So as whenever you take a distributed snapshot, you can also run this algorithm called termination detection, and it is simply going to ask a question, are you done? So you're going to, in addition to sending a marker message, you're going to send an are you done message. Okay. And you either answer yes or no to that message. Okay. So essentially when you send a message, remember in distributed snapshot, you send a marker message to all your neighbors on your outgoing channels. Okay. Here you're going to also send an are you done message to all your neighbors. Okay. And your neighbors are going to do the same thing to their neighbors and so on. And you got to wait for the responses to come back. So if you essentially get I am done from all your neighbors and you are yourself done, then you send an I am done message to your parent saying I am done, all my neighbors are done. So essentially you send that message. But if any of your neighbors says they are not done, or you are also still not done because you are processing some messages, you can essentially send a not done, or what is called a continue message. Continue essentially here means you are not finished. Okay. Done essentially means you are finished. Okay. So you either say I'm finished, and you say you're finished when you are finished and your neighbors have replied to you that they are finished, or if any one of you, your neighbors or you are not finished, you send a continue message. Okay. So essentially all these messages trickle back, and whoever started the snapshot is going to get one of two responses. All of its neighbors are going to say they're finished, and since they have queried their neighbors and their neighbors have queried their neighbors, if you get a message saying everyone is done, you can assume the computation is done. Okay? Then you can essentially shut down the system or send messages to everyone saying time to shut down. But if anyone says continue, meaning that they are not done, you say let everyone continue running, there is still more work to be done in the system. Okay? It's a very simple way of querying everyone. Okay? And the way you do is you don't actually broadcast to all the neighbors and get responses. You essentially do it hop by hop, neighbor by neighbor. That's how you are doing the query. Okay? So, very straightforward extension of a distributed snapshot algorithm. This is called termination detection. Okay? Again, this doesn't require you to have any synchronization or any of that thing sort. You do this as part of taking a distributed snapshot. Okay, yes, question in the back. Okay. Question is, when in practice would you initiate the termination detection algorithm whenever, or would you initiate a snapshot whenever you want to do termination? That's your question, right? So it doesn't really matter how you initiate it. Okay. You could say you take snapshots every hour. You could have some period, and then whenever you do that, you can also ask if they're done. Right. So the question is, do you wait an hour? So as I said last time, any process can begin a snapshot for any reason. Okay, one of the reasons to start the snapshot may be let's also check if everyone is done. Okay, you don't want to do this too frequently because you just, if processes are still processing data or doing some work, you're just wasting cycles by asking everyone and then finding out that the computation is not done. So how you initiate, when you initiate is an orthogonal issue. But there are practical considerations on, okay, if you are done, should you wait an hour before you can shut down? Should you not query them? You could. But I mean, that is orthogonal. That's how you actually use the algorithm as opposed to how the algorithm works. Okay? This question.
So this doesn't actually require like a snapshot having been made. It just requires following the snapshot process because it's kind of like piggybacking on the snapshot process.
Right. So the question is, does this actually take the snapshot or does this piggyback? So this is being done as part of the snapshot. So you will also take a snapshot in the process. Of course, you could have just done this independently of the snapshot, but because you're going to do that anyway, you can also find out if the computation is done for free, effectively, because those messages are anyway going to all the processes. Okay. Any other questions? Yes. What happens in case of a cycle? Come again, what do you mean by that?
I mean, last time we talked about we had a triangle, and it could happen due to delay that the first one sends a marker to the first node, that one sends to the third, and the third sends to the initiator. And in this case, by the definition of predecessor and successor, everyone has a successor.
So I did not define the sender and the receiver. So the node that is asking questions to its neighbors is called the predecessor. And then all the neighbors that receive these questions saying, are you done or not, are the successor. Okay? Now, of course, there could be, if you have a distributed system which is basically a set of processes communicating with one another, it could have cycles in them because there may be processes in a ring or they might have arbitrary cycles. The answer to your question is what happens in case of a cycle is it doesn't really matter. Whenever you receive a question, okay, from the first time you receive a question, that is your predecessor. Essentially, you don't have to answer that question multiple times. Okay, because you are forming a tree, overlaying a tree into this topology, okay, based on who starts it and who gets these messages and so on. And then the responses just go up the tree. Does that make any sense or it does not make sense?
And this is like on the send it done node, you can all of the successors send it done. But when I have a cycle, no one can send it done because everyone has a successor or predecessor or everyone can find it.
Right. So, okay. So the successor or predecessors are not the topology. That's how the messages are propagated. Okay. So let me show you in your example. Right. So this is the process that sends the request. It asks a question, are you done? It asks a question, are you done? Okay. And then depending on which of these receive it first, they might send a message, are you done or not? Okay. So now when this process receives it, since it has already received a message from the other node, it's not going to ask it again. Okay, because you don't actually, if you have received a question saying, are you done or not, you're supposed to send an answer, not ask a question to your parent. Does that make sense or not make sense?
Yeah.
So this is node 1. It has asked questions, are you done to these two, node 2 and 3. Okay. 3 might send a question to 2 and 2 might even send it to 3 if they happen to do it at the same time, but it doesn't matter. Once 2 receives it, it's not going to essentially send the question back and have an infinite loop, because it knows it's received a question, it's basically going to only send answers back. Okay. So that is why you will not get cycles, because you're essentially overlaying a tree on top of this topology. That's the short answer to your question, but it's a good question nevertheless. Okay. Any other questions on this? Okay, so let's move on to this problem of leader election. Okay, this is something that is a very classic problem in distributed system. Okay, whenever you have any node that is essentially a master node or a coordinator node for any specific task you are trying to perform, okay, you can either pick that node statically or you can pick that node dynamically, let the node be determined at runtime. If you are going to do it dynamically, you need a leader election algorithm to elect the leader to take on whatever task you are trying to perform. Okay. Now, when we did time synchronization, for example, okay, we essentially had this notion of a time server. That was the one that was actually broadcasting time. So you could pick the time server on the fly. Okay. When we'll talk about distributed locks in a few slides, you will see that there are coordinator processes. Those can also be chosen on the fly. Okay. In Skype, we had this notion of a super peer. Okay. If you remember what I had said at that point, the super peer is chosen dynamically by other peers in the system. Okay. You are going to use a leader election algorithm to elect a leader and make it a super peer. Okay. So essentially, a leader election algorithm is a simple technique whereby a group of nodes coordinate and then say, this is our leader. We elect that leader, and then that node essentially takes on whatever task it is chosen to perform. Okay, so let us see how do you do this. We'll see 2 or 3 different ways to elect a leader. The first one is called Bully algorithm, okay, and this is essentially a very simple algorithm where you are going to number nodes 1 through n, okay, and then we are going to use these IDs to essentially pick the highest ID process that is still up. Okay. Typically, the way you pick a leader might depend on what you are trying to do. Okay. You might say, let's pick the most powerful machine to be a leader. In things like Skype super peer, you want the node that is a super peer to also have sufficient resources to perform that extra task. Okay. So you might say, I will pick the least loaded node, I might pick the one with the most memory, one with the fastest network. You can have any criteria that you choose. Okay. In this case, we are not going to actually look at the characteristics of the node. We are simply going to number the node 1 through n and say the highest ID node that is still alive is going to become the leader. Okay. That criteria can be easily changed. Rather than highest ID, you can say least loaded or any other criteria. At this point, we are just going to start with ID, but you can use other criteria to pick your leader as well, as we will see. Okay. So I'm going to show this with a picture. Okay. So the essential idea is, here is a set of nodes numbered 0 through 7. Okay. We will assume that at some point in time 7 was the leader in the system. Okay. And the leader crashed. Okay. That is why there's an X here. Okay. So if any node sees that the current coordinator has failed, it can start a leader election algorithm saying, let's elect a new leader. The current coordinator is not responding. Okay. You also have to run leader election and just bootstrap the system. You start it up, there's no coordinator. So whenever you start up your application, you have to run a leader election. Whenever the current leader crashes or maybe resigns, you got to elect another leader. Okay. So in this case, 7 has crashed. Okay. Maybe 4 notices that 7 is not responding, so it starts a leader election algorithm. Okay. And in the Bully algorithm, it works as follows. You essentially send election messages to all nodes that have a higher ID than yours. Okay. If 4 starts an election, okay, it's going to send a message to 5, 6, and 7. Okay. In this case, 7 has crashed, so 7 is not going to respond. But you will see that 4 has sent election messages to essentially 5, 6, and 7 in this case. Okay. And the process is going to recurse. Okay. 5 is going to get that election message and say I am going to run an election. So it is going to essentially send, okay, first they send an acknowledgement, that's what is shown here. So both 5 and 6 send an OK message, which is an acknowledgement saying you got your election. And then 5 and 6 are going to start their, each of them is going to start their own election. You will see that 5 sent a message to 6 and 7. Okay. 6 sent a message to 7. So there are 2 elections that are in progress because you are recursively starting additional election. Okay. Now what 6 is going to send an OK message to 5. Okay. And then it's going to wait for 7 to respond, which it doesn't in this case. Okay. So it's when 6 sends a message to 5, 5 is going to say, okay, 6 is alive, okay, and then let 6 decide what it needs to do. And then 6 is going to try to query 7, and then it says 7 does not respond, it's going to declare itself the leader. Okay. The basic idea is, since your goal is to pick the node with the highest ID that is still alive to be the leader, if a higher ID process sends you an OK message or an acknowledgement, you know that you are not the leader because there's at least one node that has a higher ID than yours that has actually sent you an acknowledgement. So you let them fight it out and decide who the leader is. Okay? So the reason it's called bully algorithm is higher ID processes are bullying lower ID ones to drop out of the election so that they can eventually win. Okay, that's the essential intuition. Your question, yes.
So what if another node joined the group, like node 8 joined the group, the leader changed to node 8?
Okay, question is, what if a new node 8 joins the group? First of all, this is not a peer-to-peer system. Okay? It's not that nodes are joining and leaving. Just think of it as there's a set of server processes that are doing something. So it's not like you will have arbitrarily node joining. Having said that, let me rephrase your question, and you could ask, what if 7 woke up at a later time? 6 has become the leader. Maybe 7 had crashed, it reboots and rejoins. Okay? That's a valid point because 7 is already part of the system. It can restart. Okay? As we said, any node can start an election, okay? Including a failed node that comes up. It can start an election. Okay? In this case, if 7 starts the election, it's going to win immediately because there is no higher ID process it can query. So it's going to declare itself the leader and send a message to everyone else saying, I'm taking over as the leader. Okay? So the leader may change over time. Okay? At this point in time, if 7 is down, 6 has become the leader. Because by simply starting an election, 4 and 5 are going to essentially start their elections and they hear from a higher ID process, they drop out. 6 is the only one left, and then it essentially sends a coordinator message which essentially says, I won, I'm the new leader to everyone else. Okay? Yes, several questions.
I'm wondering why it's recursive. Why can't, let's say, 4 just send a message out to everybody and get a response back and then notify everybody?
Okay, so question is, why should it be recursive? Why can't 4 send a message to everyone, get a response, and send? That's the next algorithm. We'll come to that. All right, yes.
There's a network delay and both 6 and 7 both say they are the leader.
What if there is a network delay? 7 is currently down, so we don't have 7.
Like when you get back and there's a network delay, there's a connection.
Right. So question is, what happens if 7 comes back? Is that your question? What do you mean by network delay?
Like there's a scenario where the network delay is really high and the 6 doesn't receive the message from 7, but others receive. And
Okay. So you are saying, what if 7 was actually up? 6 just hasn't received the message from 7, right? So first thing is, you are assuming that the network is reliable. Okay? Your timeout is well chosen. If your timeout is poorly chosen, where you think that 6 is not responding before 6 actually responds, because 6 could be slow, the network could be slow. Okay? Then you are going to get a situation where temporarily 6 becomes the leader. Okay? It's going to broadcast its message to all the nodes. But 7 could say, if 6 has become the leader, it could start a new election saying, I'm still a higher ID process than 7 and then 6. It could start a new election and then it will take over after some time. Okay? Eventually, you will have the highest ID process. Okay? But having said that, part of the algorithm depends on if you don't hear back from a node, okay, you assume it is done. And this is not a problem specific to leader election algorithm. Okay? This is a problem with any distributed application where you are asking, how do you set the timeout? If I were to rephrase your question, you are going to say, how do you set a timeout so you know that the other end is not responding? Okay? And that's a very important and classic problem in distributed systems, because you cannot actually distinguish between a node that is down and a node that is very slow. Okay? Because you can set any timeout, but think about a node that is actually slow enough that it takes longer than that timeout to respond. Okay? So it is very hard to actually distinguish between a failed node, because a failed node is an infinitely slow node, if you think about it, right? Because it's not responding. But then you could have a node that is so slow that it takes a very long time to respond to your message. Okay? So this problem of how do you set a timeout and how to determine whether the timeout is valid is actually a more general problem. It will arise here also. Okay? We assume that in most cases a reasonable timeout value will work. Okay? And if it doesn't, so be it. That node can always start an election and bully 6 out and say, I am taking over. And that will be it. Okay? So in this case, the effects are not going to be harmful. But what you raised is a very important orthogonal question. Okay? Yes? Is there any state migration? Okay. So if you change the leader. So now all we have done here is elected a leader. Okay. Once you elect the leader actually has to do something. Okay. Whatever it has been chosen to be the leader of. Okay. If that process involved having state, okay, then the state has to move from the coordinator that has failed to the coordinator that has taken over. And we'll soon see a distributed lock where the coordinator keeps track of whether the lock is free or in use. Okay. And if the coordinator crashes, that state better be saved on disk, because otherwise if it was in memory, that state is lost. Then you don't know what to do. Okay. So that's all orthogonal to the leader election. Okay. If there's a new coordinator, the coordinator has to bootstrap and take over whatever the old coordinator was doing, get its state back. How do you do that? That depends on what the coordinator was doing. That depends on the technique you are trying to develop, not the leader election itself. Okay. Some questions here. Yes. Yes. Okay. So what if the network partition? So that's a good question. If you have two partitions, not two partitions. If you have partition and have two groups, okay, then you are essentially going to have a scenario where there are some nodes on one side of some node on the other side. They might each start a leader election and pick a leader within their group. Okay. It's not an ideal situation. Okay. But then I'm assuming in that case, whatever application you have either is robust to handling that case or not robust, so it's as good as having a dead application. Okay. But you will have that problem if you essentially have a network partition where some nodes are on one side of the network and other nodes are on the other side. That's a problem, not specific to leader election. It's a problem in general for a distributed application. Okay. This question in the back. Okay. Question is, what is the condition that an election start? An election can start for any reason. Okay. Any process can initiate an election for any reason whatsoever. Okay. You not heard from the current coordinator in a while. Okay. You maybe try to ping it, it doesn't respond. You can start an election. You can start an election for no reason at all. Okay. Maybe the same process that was the leader will get re-elected. Okay. So why we start the election is orthogonal. Typically, you will start the election if you have not heard from the coordinator. You suspect that the coordinator has crashed. That's a good enough reason to start an election. Okay. You could also ask who can start the election. In this case, any process can start the election. Okay. The reason we don't say if the node coordinator crashes, process 1 should start the election, because we don't know, process 1 may crash as well. Okay. So we let any node start the election and we let it start for any reason that it decides is the time to start an election. Okay. So those are all implementation issues in some sense. Okay. Once you decided that you want an election, then this is how it would work. Any other questions? Okay. So it should be clear that this technique has order n square over it, because it's recursive. So if the worst case is when the lowest ID process starts an election, it's going to send n minus 1 messages, then n minus 2, and then there will be more messages recursively, and you will get order n square over. Okay. We'll see how we can do better than this. Okay. So the next algorithm is what was actually mentioned, which is ring based. So here you're not going to send recursively have elections. You're just going to take the IDs of the process and assume that they are form a ring just for the sake of leader election. Okay. The ring is not used in the application itself. Okay. But if you number them 0 through n for purposes of leader election, okay, you will say that I will have two neighbors, I plus 1 and I minus 1, okay, mod n. So this is again shown in the picture here, which is the same scenario. Okay, now 7 is down. In this case, 5 decides to start an election, and in this case, you will see that 2 also started to do an election. Okay, multiple nodes didn't hear from the coordinator; they started an election. That's okay. Okay, we'll assume that every election has a unique election ID, so you can track which election you are replying to. Okay, you can have multiple elections concurrently. It doesn't really matter so long as you can figure out which message is for. So all you do in the ring election is, if you are alive, you get an election message, you just append your process ID and send it along. Okay? And by appending the process ID, you are saying I am a process that is still up and running. Okay? So all this is doing is querying every node in the system saying are you up or not. Okay? And essentially if you receive this message, you are going to append your ID and send it to your next neighbor. So in this case 5 appended its ID, sent it to 6. Okay? 6 tries to contact 7, sees that it doesn't respond, it appends this message and eventually it goes to 0, which is the next neighbor, and then 0 appends this message, goes to 1. So your message is going to circulate through the ring, okay, and then come back to the process that started that election, which is 5. Okay, 5 will look at the list, which is the list of all processes in the ring that are still up. It will look for the max ID and declare that process to be the leader. So there will be another message that will circulate through the ring saying this is the new leader. In this case 6 is going to get elected as the leader. Okay? And you will see that 2 has also started an election message. That message will also propagate through the ring, go back to 2, it will have the same end result. Okay? The only thing is you got to distinguish that there are multiple elections in progress. It doesn't really matter. Yes, question. Yes. Go ahead.
Couldn't it actually be a problem if the network topology changes while there are 2 elections going on?
Yes. The question is, could there be a problem if there is a network topology change while there are 2 elections? Let me simplify that question. It says, what if the network topology changes while a single election is going on? Okay. So what if the election message went by, okay, and then some process actually crashed? What if 6 crashed after it said it was alive? Okay. So you might declare 6 to be a leader, but 6 has also gone down. Okay. So the election algorithm only yields a good result if there is no change in the network while the election is in progress. Okay. But if 6 becomes the leader and you basically don't hear from 6, you can always start a new leader election algorithm. So that's the short answer. But of course, you might have a end result where you elected a node that is dead to be the leader, because the node died after it actually voted that I'm alive. That can happen as well. But you basically, since you can start multiple elections, since you can start elections at any time, eventually you will find a leader. Okay, maybe the first time you got a bad result. Okay, yes, question.
Why couldn't we just, this is still going around one by one, trying to get a message to propagate. Couldn't you just have, say, 5, send a message to everyone saying, please respond with
Yes.
the leader, and you get one message back. It's like, instead of taking the round trip time, like wait for everybody to propagate.
Right. So the question is, you could, so what you are suggesting is a different technique where one process asks all other n minus 2 in this case processes, it gets a response and says that's the leader. Okay. You could do that. Okay. In this case, the advantage is you only need to know the ID of 2 other processes in the system rather than every process. Okay. In the bully algorithm, you anyway knew the IDs of every process because you had to actually broadcast to all the higher ID process in the first phase and all the lower ID processes in the last phase when you declare the lead. So there you actually needed the IP address of every node in the system, which is a disadvantage incidentally, because if your system is large, it has 10,000 nodes. When you declare your result, you are going to send 10, one node has to know all IP addresses of everyone. Here you don't need to do that, you only need 2 just for leader election. So that's because you need the left neighbor and the right neighbor. And you need, actually you don't need 2, you need more than 2 depending on how many concurrent failures you can have. Okay? Because it's no longer enough for you to know just a left neighbor, because if left neighbor crashed, you have to jump over. So you can say I can tolerate at most n concurrent failures, so you need to know n plus 1 neighbors on each side. Okay, so but that's still smaller than the size of your system. That is why it's a little better. Other than that, they do the same thing. Okay, this actually has higher delay because you got to propagate through the ring. Any other questions here? Okay, so that's your ring algorithm. Okay, so we'll just do a very quick comparison. So bully algorithm, worst case is initiator of the algorithm is the node with the lowest ID, triggers n minus 2 elections, that's order n square messages. The best case is essentially the node with the highest ID process starts an election, it declares itself to the leader. There's only n minus 1, n minus 2 messages just announcing the result. Okay, so you will be somewhere in between. Okay, in general, in the ring it's always 2 times n minus 1 because you will have to propagate through the ring twice. Okay, so it's slightly different complexity, but there will be higher latency typically in the ring because you're circulating through n rather than querying the highest ID processes all at once. Okay, so but beyond that, the message overhead of ring is going to be a little better in some sense, quite linear. Okay. Now, there are many leader election algorithms. Okay. This is still an area of research that you will see papers appearing in. In many cases, there are all sorts of special cases where, let's say, you have wireless networks. Okay. So the way you will have to do leader election has to be limited by topology in the network. Things that we said we could do on a wired network no longer hold because your wireless network essentially says that you can only communicate with any node who is in your range, wireless range. Okay. So you can't arbitrarily send a message, at least not directly, to some arbitrary other processes. So you always have to essentially form a topology based on who you can communicate with, who is within your range, and those will actually propagate to other nodes and so on and so forth. That limits how you take either the ring algorithm, bully algorithm, and actually implement it. Okay. For example, you can't simply send one-off messages saying I won in the bully algorithm to every node in a wireless network because not every node may be within your range. You still have to propagate it through other. So as a result, those algorithms, which are very simple ones, have been modified to essentially fit different scenarios. In this case, the scenario is nodes. Some nodes cannot directly see other nodes. Okay, you have to essentially communicate with other nodes. So that gives you some sort of a tree which says who can talk to whom, who is within range of whom, and then all your election essentially has to use that topology to figure out who is up, who can be declared the leader, and so on and so forth. Okay. So that's one special case. Okay. The other scenarios are you are not really going to use IDs to elect leaders. Okay, because that's a kind of meaningless metric. You are going to say least loaded process, okay, or the one with the most amount of resources in the system and things of that sort, which means that your leader election algorithm has to be more sophisticated. Okay. The bully algorithm is not going to work because you can't order nodes by their load, okay, because in that case the one with the highest ID process always wins. Typically, if you want the least loaded process to win, you want to use something like ring where you query everyone, okay, find the load and then pick the one with the least load and things of that sort. Okay. So there are many subtleties that are going to arise in practical algorithms, which we won't go into here. I just wanted to say that there are all sorts of things you are going to see if you start looking for lead papers on leader election. Okay. And basically they depend on the characteristics of the system and what you are trying to do. What kind of leader do you want to elect? Typically, it's not the one with the highest ID. You want some other characteristics. Okay, so not going to go into that technique. I do want to say a little bit about super peer leader election because that is where what I just said applies. Okay, if you remember in Skype, okay, I said that there are groups of Skype nodes, and each of them will elect a super peer that's going to answer for all of the nodes in that cluster. Okay, the super peer is representing other nodes in its group. Okay. So in this case, essentially the Skype nodes are going to run an election and pick one node. Okay. This is not done in the current architecture of Skype. This is how the old architecture worked. Right now, they are essentially going to use cloud servers to do all of the hard work for you. The peers are not going to do the work. Okay. But at one point, the system was fully decentralized. There were no centralized servers. Okay. So to discover which nodes are up, are your friends currently logged into Skype, all of that information was kept within the Skype network itself. and specifically within super peers in Skype that were tracking which nodes are up, what is it that you're logged in as, who are your friends, are your friends currently logged in, all of that was maintained by Skype, super peer. Okay? So it was important for you to have these characteristics that your essential super peer should have low latency access to other nodes in their group so that they can communicate with them. Okay. Super peers should be evenly distributed in the system. Okay. Depending on how many nodes there are in your network, okay, you want them to be evenly distributed so that any node, Skype node has a super peer nearby so that it can communicate with that super peer and so on. Okay. There should be some fraction of super peers relative to the number of nodes. As the number of nodes grows, you also elect more super peers. Let's say you want 3% of your nodes to be super peers. Okay. So if you have more nodes joining, then your super peer number of super peers is going to increase. Okay. Here you don't have one leader across the whole network. You have one leader in each group. Okay. And that leader is your super peer. Okay. And then you also don't want the load on the super peer to be high. So the size of the group is limited. There's a max limit. Okay. So now you can imagine constructing a leader election algorithm that has to satisfy that property. You'll see that's no longer as trivial as your ring algorithm and things of that sort. Okay. You've got to figure out all of those things. Okay. Which is the node that has the best connectivity to other nodes in the group? Which is the node that has the most resources? Okay. And then how to form the groups themselves, okay, so that the groups are relatively coherent in terms of their topologies and so on. Okay. Is there a fixed number of super peers in the system relative to the number of nodes? Can you dynamically increase the number of nodes and hence increase the number of super peers? So it's actually much more complicated than what we have done. Okay. It is just to give you some notion of in real systems, there are very sophisticated variants of the leader election algorithms we have seen. Okay. We won't go into the Skype super peer algorithm. In fact, it's not published, so nobody actually knows exactly what they did. They tried to guess, but that's basically a guess. Okay. But these were some of the properties that they were trying to achieve when they tried to do the super peer structure. Questions on this? Okay, so there is some more material in the book. I'm not going to go into that. You can go and look at it if you are interested. It gives a little more details of what they did, not all of it. Okay? But instead, we will switch gears and you move on to the next module, which is distributed synchronization or locks. Okay? I presume all of you have used or know about locks in a centralized single process application. Okay? If you are threads, you must have used a lock. Okay. Locks are used to guard shared data structures, used for synchronization and so on. Okay. Now think about a scenario where you have n processes in the system. They are trying to coordinate something. Okay. And you have to implement a lock. How are you going to extend this notion of a lock that you had in a single process, but then make it work across processes and across machines? Okay. That technique is called distributed synchronization. Okay. We will see 4 different methods here. Okay. Some will be centralized, some will be decentralized. We'll look at properties of the centralized versus decentralized. We'll look at complexity, message overhead, and all of these things. Okay. Is the problem clear? Okay. You have n processes in the system, okay, and they have to use a lock to coordinate something. Let's say they want to access a file. Okay. You want to essentially grab a lock on a shared file or a shared data structure before you access it. Okay. Except that these are processes on multiple machines, so you can't use lock inside a single process to do this anymore. Okay, you've got to extend that abstraction to multiple processes. Okay. So the first technique is going to be very simple. Okay, we are going to use a centralized approach. So we'll assume that processes are numbered 1 through n. We'll pick the highest ID process to be the coordinator. Okay, we are going to run leader election and pick the highest ID process to become the lock manager. Okay, the coordinator in this case is a lock manager. It is going to keep track of the state of the lock, who has the lock, decide on granting access to locks and so on. Okay. And the process of grabbing a lock is very simple. You are going to send your lock request to the coordinator. Okay. If the lock is in use, your request will be queued. You will be blocked waiting for a reply. This is the same thing. If you do lock.acquire, and if the lock is in use, your thread will block until the lock is released. Okay? You are essentially the same abstraction here. You are going to send a lock acquire request to the coordinator, and if you don't hear back from the coordinator, you assume that the lock is in use, so you just have to wait until the lock becomes available. Okay? And at some point in time, the coordinator is going to essentially send you a grant message which says you have the lock. At that point, you can unblock and enter your critical section, do whatever you need to do. Okay? And at some later point, you are going to essentially release the lock and send back a request to the coordinator. Okay? So your coordinator process is essentially going to do all of the work that a typical lock manager or a locking library would do. Here's a picture. Okay? 4 processes, 0 through 3. Okay? We pick 3 to be the lock manager. Okay? The lock manager is going to have 2 things. It's going to have a queue, and it's going to have the state of the lock. The state of the lock is free or in use at any given time. Okay? So initially, 1 sends a request saying I need the lock. Okay? That's a lock acquire request. Okay? 3 says the lock is free, so it immediately grants the lock. Okay? So now 1 essentially holds the lock. Okay? Now if 2 sends a request for a lock, okay, since the lock is in use, it's going to that request is going to be put in the queue. Okay? And 2 will have to block because it has not gotten any reply yet. Okay? Because it's going to wait. Okay? At some later point, when 1 releases the lock, okay, you are going to look at your queue. If the queue is non-empty, you take the request at the head and grant it the lock. Okay? If queue is empty, the lock state is changed to be free. Okay? This is how you would implement any lock, except that now you do it in a distributed system. There are messages going over a network to ask for a lock, to get the lock, to release the lock, and so on. Yes.
How do you use some process that crashed when it acquired the lock,
Okay.
failed to release the lock?
Okay, so that's a good question. The question is how would you deal with failures in the system? So that's really where the problem arises. Okay? This is, see, looks trivial, but it's not really trivial. Okay? Because you might say, okay, what happens if 1 crashes after it gets the lock? Every other process that is actually waiting for a lock is going to wait forever, because a lock is never going to be released. Okay? Yes. Okay. So you could, as is being suggested, one way around it is you are essentially going to change the semantics of a lock. Okay. Typically, if you write correct code, you can grant the lock, and whoever is holding the lock can hold the lock for as long as they wish and release the lock when they are done. They are not given a time quota saying you only have it for 13 milliseconds. Right? But in this case, because we are in a distributed system, process crashes can cause problems. Okay? If you have a single process and threads, if 1 thread crashes, it's going to take down the entire process. Everything else will crash with it by definition. So there's no other process that's going to, no other thread that's going to wait, because 1 thread crashes the whole process. Here that's not the case. 1 process crashes, other processes are still running. Okay? They might have to wait forever. So what could you do? You could put a timeout. Okay? You could say, I grant the lock, but you are given an expiration time. You can always renew it, saying my time is running out, but I need it for another block of time. Okay? But you got to do that extra work. That has changed the semantics of the lock. Okay? You no longer have a lock acquire, and then you wait until the lock is released and you hope that everything is fine. Okay? So yes, you could do that. In fact, that is what is done in many cases, because otherwise, if the client crashes, then you are done for, because you are going to essentially, all the other processes are just going to wait forever. Okay? So the other question, what would you do if the coordinator crashes? You had a question.
Yeah, so if process to ask for permission at a simple region, and as it is waiting, then maybe process 4 also asks for the same permission.
Okay, so question is, if 2 is waiting, some other process can ask. So multiple processes can request a lock. If the lock is in use, they'll just get queued up. Okay? So if 0 asks for the lock now, it will get queued up here. Okay? So it will also block, and then you will grant the lock 1 at a time. Okay? There's no problem in multiple processes requesting the lock concurrently. Only 1 process can have the lock. Everyone else has to wait. That's not the problem. That's easy to deal with. The problem is, what do you do when there are crashes? Yes.
Is there a possibility that you could have like a timeout for the lock, and then the process doesn't fail, but the timeout ends the exact same time that it would release the lock, and so there's kind of like ambiguity
Right. So the question is, what if you put a timeout and the timeout actually expires around the time you would have released the lock? Okay, if you change the semantics of the lock, you got to actually change how locks work to begin with. If you start putting a timeout, okay, you could always ask, can I write a program where the critical section takes longer than the timeout? How do I do that? Okay, if I say you have 10 millisecond timeout, you could say I have much longer critical section. I am doing a database query. I need the lock for 20 milliseconds. How are you going to deal with that, right? So either then you have to have a way to renew the lock while you hold it. Okay, that means you get it in 10 millisecond chunks, or you got to make a critical section smaller. The critical section can never be longer than 10 milliseconds. Either way, you got to change the code. Okay? So it changes the semantics of how you are used to dealing with locks. Either way, if you're going to do these kinds of things. Okay? The other thing, as I was saying, is it's not that a process that's holding the lock can crash. The coordinator itself can crash. Okay? So you might say, fine, 3 crashes. I'll run a leader election, elect a new leader. Okay? But do keep in mind that the lock has a state in this case. Okay? The state of the lock is whether the lock is free or in its use, and there's a queue associated with the lock which says who is all waiting. Okay? If that state and this queue is maintained in memory and 3 has crashed, you elect a new leader. That leader needs a way to reconstruct the state of the lock. That's not trivial. How do you know who holds the lock if a new leader is elected? Okay? Are you going to go ask everyone, do you hold the lock? That's again changing the semantics of the code. Okay? If a thread is holding the lock, it doesn't expect another thread to ask, do you hold the lock? Okay? That doesn't actually work very well. So you got to keep this state in a persistent fashion. You might actually log everything to a shared disk or a shared file system, so that if a new coordinator takes over, it goes and reads the lock and says what has happened, what is the current state of the lock. Is it in use, who is holding it, what processes are waiting, so that it has the same information that 3 had before it crashed. Okay? Again, that means there's extra work to be done. Okay? You got to keep information on disk, which you didn't have to do if you had, let's say, Java locks or things of that sort. Okay? This is to deal with failures, because that's where all of this gets complicated. Okay? Yes, question.
So what if we elect another node as the coordinator?
What if you, yes?
The first node and the second node all send request to the third, the coordinate number 3, node number 3, and the request has been queued, and then we elect another node as the coordinator.
Okay, the question is, if you have a queue of requests, threads or processes waiting for the lock, what if you elect a new coordinator? That's your question. Okay. You typically you do that if that coordinator actually failed. Okay. And then if the coordinator failed, if you elect a new coordinator, that coordinator has to reconstruct the state of the lock. Okay. Lock is a stateful entity. Okay. It has basically you have to keep track of, is the lock available or not? Is it been granted or is it free? You also have to keep track of that queue. As I was just saying, the way you will have to do it is you will have to log it to disk, because the process crashes, his memory is gone. Okay, so you got to keep that state on disk in order to reconstruct. So things get complicated when you do distributed locking. Yes.
Is it possible that you replicate states of free to synchronize the replication with other coordinated?
Yes. So question is, could you have replicated this? I'll talk about a scheme where you have multiple coordinators, which are basically the state of the lock is replicated on multiple nodes to deal with that problem. Okay. Any other questions here? Okay. So this is a centralized algorithm. Okay. So in addition to all the failure issues, even if there are no failures, you might still have a centralized coordinator become the bottleneck. There may be many locks, maybe hundreds of locks in your system. There's one node that's maintaining all of that lock state. So you might actually have problems with overload and things of that sort. Okay? But let's look at the properties. So it basically looks like a normal lock except in the failure case. Okay? Here we'll say that the centralized lock is fair because it's granting locks in the order in which requests were received. It has a FIFO queue. Okay? So it is fair. No process is getting any more favors than other processes. Okay? The network overhead is simple, okay, because there are only 3 messages. Okay? Requesting a lock, okay, granting a lock and releasing a lock. So only 3 messages to implement the whole scheme. Okay, the shortcomings are there's all these failure issues. Single point of failure, dead coordinator is going to cause problem, dead clients are going to cause problems because they will never release a lock. So all of that is where things are going to get more complicated. Okay? But there's no right answer to how to solve that failure issue. That is going to be implementation specific. Are you going to change the semantics of the lock? Are you going to put timers and all of those things? Okay, so now let's look at a decentralized approach. Okay. So in this case, we'll do whatever was just being asked, saying every node, okay, every machine in the system also has a coordinator replica. Okay. So you have a coordinator running on every node on the system. Okay, n nodes, there will be n coordinators as well. Okay. So if one coordinator fails, you will have other coordinators still doing the work. Okay. So now what that also means is your lock request has to be sent to all nodes. You are going to broadcast it, actually multicast it. Okay. And then you have the coordinators vote. Okay. And then essentially you take the majority. The vote is essentially whom to grant the lock, whether to grant the lock. Okay. So essentially every coordinator is going to run the same algorithm as the centralized algorithm, and then it will tell other coordinator, I think we should give the lock to node 2. Okay. They will all vote. If there's a majority agreeing, then you just say 2 gets the lock, and so on and so forth. Okay, now even if one coordinator crashes, that doesn't impact anything because the other coordinators can still vote. They're still tracking the state of the lock. They're still maintaining the queues because you're essentially replicating the state of the lock and multiple machines in the system. Okay. You don't actually need every node to be the coordinator. That's the degenerate case, but you need more than one coordinator. Okay. You can have k coordinators in the system. They're essentially going to all replicate the state of the lock. Okay. And they're essentially going to use majority vote to figure out what is going to happen, whom to give the lock, and so on. Okay. So that's the basic idea. Okay. Now the things will go wrong only if lots of coordinators all crash. In particular, okay, if the majority of the coordinator crashes, then you can no longer have a majority vote. Then your lock will fail by definition. Okay. So this assumes that essentially you can tolerate up to k concurrent coordinator failures without still impacting the lock state, so long as k is less than the strict majority. As soon as more than the majority of the coordinator crash, then basically your lock will not work because you always need a majority vote in order to decide who gets the lock. Strict majority, more than 50%, more than half. Okay. So don't worry about all the rest of what is being said there, but that's the basic idea of how the lock is going to work. You're going to replicate, you're going to use voting, and you're going to take majority vote. And then that allows you to tolerate a minority of the coordinators crashing. You don't have to do all the recovery because everyone is already tracking the state of the lock, because every request goes to all coordinators. So every coordinator knows what is happening. Okay. So simple replication is what we have done of the coordinator. Is this clear? The decentralized algorithm, okay, is using the same idea as the centralized, but doing it on more than one node. Okay. Here's a different one. Okay. Another decentralized algorithm. This one is actually going to use Lamport's clock. Okay. The way it's going to work as follows. So here we are going to use the notion of event ordering to decide whom to grant the lock. Okay. Essentially, we are going to use Lamport's clocks. Every time you want to request a lock, you are essentially going to send a message with your Lamport's clock value. You are going to use Lamport's clock to order messages. So if there are multiple concurrent requests that arrive, you are no longer going to do FIFO. You are essentially going to grant locks in Lamport's clock order. Okay. Because FIFO is going to favor the node that is closest to the coordinator. When there are concurrent requests, the message that goes fastest to the coordinator is going to get the lock. If there's a node that is far away, message takes longer, it's going to lose even though it may send the message before. So let's use Lamport's clock to order. Lamport's clock says this is the order in which they were sent. We'll grant them in the order in which they were sent. Okay. So essentially that's the basic idea. So here's how it's going to work. Okay. Process, in order for you to grab the lock, you're going to do the following. You're going to increment your logical clock. You're going to request a lock by broadcasting that request message to every other process in the system. You are going to say, I am process K, this is my clock value, and I am requesting the lock. You broadcast that to every other process in the system. Okay? And you have to wait for a reply from every other process before you can enter a critical section. Reply is essentially that process is granting you permission to enter the critical section. So you ask everyone, if everyone gives you permission, you enter the critical section. Okay? That's the rule. Okay? Now, when do you send reply messages? Okay? If you are a process that got a request from some other process J, if you don't have any contention for the lock, you don't care about the lock, you send a reply saying, go ahead, I don't care. Okay, so you basically send a reply. Okay. If you are already holding the lock, you are going to queue that reply. Okay. You are going to say, I am in the critical section, I am not going to grant you permission. Because by definition, you hold the lock, you can't grant someone else permission to enter. Okay. Now, so these are the lock, you don't care about the lock or you hold the lock. These are two cases. The third case is, you are also contending for the lock at the same time with this other process. Okay? That process wants the lock, you want the lock, you have sent your own request messages. So in this case, you are going to use Lamport's clocks to decide who wins. You are going to get an event ordering, say who sent the reply first. That's the process that is going to win. And how do you decide who sent the reply first? You basically order them by Lamport's clocks. Okay? And whoever has the lower of the two Lamport's clock value, basically you look at the timestamp. Okay, Lamport's clock is a form of a timestamp. Say the one with the lower timestamp gets to go first. Okay, so that's what it says. If you are contending with another process, you are going to grant its permission if that process has a lower clock value. Otherwise, you enter. You don't send, and that process is going to be forced to send you a reply. Okay, and that's it. So you are essentially now going to run this algorithm without a coordinator. Every process has to participate. To enter a critical section, you ask permission from every other process. Okay? You wait for every process to grant you permission. Okay? Not a majority, every single one to grant you permission. And you are going to get a reply if that other process is not contending for the lock. You will be blocked if the process holds the lock until it is unblocked. At that point, it will say go ahead. And if you are contending with another process, the one with the lowest Lamport's clock is going to win. Everyone else waits, and then you can give permission to the next one else. Yes, question?
So the Lamport clock here, is it a vector or is it an integer?
Okay, question is Lamport's clock vector or integer? Doesn't really matter. You can actually use Lamport's clock with the tie-breaking rule, which gives you a total order. Because the order is actually arbitrary. Just want some order. Technically, Lamport's clock gives you partial order, not a total order. But as I said, as we talked about, if you use the process ID to break tie-breaking rule, you can impose a total order on a partially ordered set of events. Okay? So you can just use Lamport's clock. You don't need vector clock.
So suppose you use a vector clock, is it possible that a process receives two vector clock that it cannot compare the
Yes. So the question is the following: if you use vector clocks, what if the process receives two vector clocks that are not comparable? Okay? So if you get two vector clocks that are not comparable, they are concurrent event. You still need a tie-breaking rule. A tie-breaking rule could still be the same, saying you take the process ID and the one with the lower ID wins. That's what we did in Lamport's clock as well. We used the process ID as the tie-breaking rule. So for every time there's concurrent event, whether you're using logical clocks or vector clocks, you get to have a tie-breaking rule to impose an order, because technically there's no order. So you will say the one you take I and j, these are process ID, I less than j, I wins. Okay, arbitrarily, there's no real reason it wins. Okay? Yes? Will there be a starvation problem? So if there are no failures in the system, okay, locks are going to be granted in Lamport's clock order. Okay? Eventually you will get a lock. This is true in any locking case. Right? So there's not going to be starvation in the non-failure case. All the problems are going to arise when there's failures, which we'll discuss in just a second. Okay, yes?
Would it be possible to construct starvation in using vector clock?
Could you construct starvation in case of vector clocks? How would you do that?
Tied by the process ID, and these two vector clocks are never comparable because they never communicate with each other, or
So the only starvation case you can think of is a lower ID process repeatedly asks for a clock, for the lock. Right? However, you will essentially have a greater vector clock value every time you do ask for the lock. So you shouldn't actually be favored if you keep requesting the lock over a higher ID process, for example, because eventually your clock value will be higher. Because you are broadcasting all of these messages, so eventually some of them will become comparable. Okay?
Okay, so you're broadcasting to all of their clocks.
Yes, because you are going to send a request to all processes, so they will actually have to do max every time they get a message, because running vector clock on top or Lampert's clock on top of this.
Okay.
Right? So, okay. So now let's ask, so this is a nice decentralized algorithm, no coordinators. You're using Lampert's clock, so everything looks good, except that you have to ask what is going to happen when there's failure. I'm going to skip this slide because we actually talked about it. Okay, so now the problem with this approach is there are not one but n points of failure. Because you have to wait for a reply from every process before you can enter the critical section. Every process has to grant you permission before you know it's safe to enter the critical section. Even if one process does not grant you that permission, you cannot enter that critical section. So now if one process fails, by definition is going to stop responding. Okay? So any process that wants to enter the critical section will be blocked forever, because it's not going to get at least one of the replies it needs. Okay? So in the centralized approach, if a coordinator crashed, then there was a problem. Okay? In this case, if any process crashes, there is a problem, because you actually made, from a failure perspective, you actually made the decentralized algorithm worse than the centralized one, because you introduced n points of failures rather than having 1 point of failure. Okay? Typically, when you go from centralized to distributed, things get better from failure resiliency perspective. It's a rare case when you actually made things worse from a failure. Generally, things are good except when there are failure. Okay? The second is all processes are involved in all decisions. Every process has to actually tell every other process whether it grants the lock and so on. So there are a lot more messages going back and forth. In the coordinator, you just ask the coordinator, it tells you what to do. Here you would ask every process what to do, and they respond to you what to do. Okay? So there's also higher load on all of the processes because you made everything decentralized. Okay? So this is just a counterintuitive scenario where your decentralized approach has higher message overhead, more complexity, and more points of failure than the centralized approach. Okay? It doesn't make any of those problems better, it actually makes them somewhat worse. Okay? But having said that, you have to still you can get rid of the coordinator and do this using Lampert's clock and so on. Okay? This algorithm, by the way, is called Rickert and Agarwal algorithm. That was the paper that proposed it. The technique is actually named after the authors of the paper. Okay? And it should be clear that it has a 2n minus 1 or 2 times n minus 1 over it, because you are asking everyone and getting back replies. There are n. Okay, so you assign n minus 1 request messages, you get n minus 1 replies. So the complexity is 2 times n minus 1 as opposed to the centralized one where it was 3. Okay, question?
So as compared to the centralized one, rather than creating n coordinators, won't you just replicate the state at n nodes and keep just one coordinator? So reducing your point of failures to actually just one.
Yeah, so that was this case. Somewhat like this case, because you were just using, it did replicated the state, but it added voting. It was not just one coordinator, it added a voting so that if there's failure, you can immediately rule out the coordinator, not have to deal with recovery and so on. Okay? So what you said is the middle technique I presented. Okay, so one more to go. Okay, this one is called token ring. Okay, here again essentially this is a slightly different implementation of a lock. You number all the processes. Okay? So logically they are going to be made into a ring. Okay? Physically they may not be a ring. As you see, this may be the physical topology. They may be part of some Ethernet or something like that, but you are going to number them and they are going to communicate essentially in a ring topology. Okay? And the way, so there's going to be a special message called a token message that's going to circulate through the ring. Okay? If you want to enter the critical section, you have to do nothing but wait for the token message to arrive to you. Okay? And once it arrives, you have essentially the lock. You can do whatever you want, and then the way you release your lock is you send the token message to the next process in the ring. Okay? So your token message is essentially granting you the lock. Okay, so essentially they think of this special message that's just circulating through the ring. If it comes to a process it doesn't need the lock, it just sends it to the next process. Okay? And it keeps circulating, and someone needs the lock. When the token message comes, they hold on to the token, they don't send it, they do whatever they are trying to do, enter the critical section, and then once they are done, they send the token message to the next node. Okay? So that's essentially how this technique is going to implement locking. Okay? Now there is a side story to why this is done this way. Okay? Essentially this token ring algorithm was part of a protocol called the token ring protocol. Okay? Back in the days when LAN technology was still evolving, there were two competing approaches. There was Ethernet and there was token ring. Okay? You probably know what Ethernet does. So what token ring did was essentially it took all the machines in the LAN, all the PCs in the LAN, and it put them in ring topology. Okay? And essentially for your network card to transmit on the network, it had to wait for the token message to arrive. Okay? Because if multiple nodes try to send message on the network at the same time, because it's a shared medium, the messages would collide. Okay? And they would get garbled. So whenever you have a shared network, only one node can transmit at any time. Okay? And to transmit, you have to essentially grab and lock on the network, so to speak. Okay? If you know what Ethernet does, it uses a randomized algorithm. It transmits. If there's a collision, it does a random back off and then it tries again. Okay? Because nodes might back off by random amounts. If you don't have too much traffic, eventually things will work and your message will get through. Okay? This uses a deterministic algorithm, not a randomized one, where you have to wait for a special message to come, and that message is, because there's only one token in the entire network, if you grab the token, you hold the token, you know no one else has it, so no one else can transmit. So you are the only node that's sending out packets at that point. Okay? So the idea actually came from a LAN protocol, and the notion of having the token was allowed you to grab a lock on the network, so you are the only node transmitting at any given time. And if you have to transmit, you have to wait until the token circulates to you. Okay? So there are all these interesting things, and this is where some of the timeout issues also came about. Okay? In the original LAN protocol, if you had lots of data to send, you couldn't hold on to the token for long periods of time. You had a time slot. Okay, you can only hold it for 100 milliseconds. If you have more packets to send, you send the token, wait for it to come back. This allowed fairness, because otherwise if you are sending a lot of data, other nodes are waiting to transmit. It might take a while for them to get their packets out. Okay? In normal locks, you don't actually have a timer, okay, other than the failure case. Okay? And because in the LAN protocol, there were timeout timer which said this is the maximum amount of time you can hold on to the token, you could easily detect the loss of a token. Okay? So if you could hold it for a max of, let's say, 100 milliseconds, and there are 10 nodes in the network, if you haven't seen the token in 1 second, you know the token must be lost, because every other node can hold it for a maximum of 100 milliseconds. Because all token ring protocols have to deal with token regeneration and token failures. Okay? Because if you hold the token and you switch off the PC, the token is lost, because you can't send it onwards, you are holding the token. Because you can assume that users will do whatever they want, right? So then if you can't regenerate the token, now no one can transmit on your LAN. You are going to be stuck because somebody turned off the PC, so you can't browse the net. Okay, so these things can't happen. So you got to regenerate the token. But there was built-in techniques that said, I can regenerate the token if I haven't seen it in the maximum timeout value, which is the timeout, the max time you can hold the token on each node times the number of nodes. Okay? Now if you are using this for real locking, you can't do that, because you cannot assume that I will grant you the lock for 100 milliseconds. What if your critical section is longer? What if you need more time? So you cannot actually bound the time it will take for the token to circulate once in the ring, okay? Which you could in the LAN protocol, but in this case it's slightly more complicated. Either you have to artificially impose a limit, say you cannot hold the token or a lock for more than such amount of time. Then you have the same technique as the LAN protocol. But then your code has to make sure that you can never hold the lock for long critical section. Okay? Or if you don't do that, you allow for arbitrary times for which you can hold the token, the recovery is more complicated. Okay? If a node crashes holding the token, how do you know that the node has crashed. What if it was actually holding the token for a long period of time? So token recovery becomes more complicated. Okay, so you are going to have some trade-offs. Either you make fault tolerance simpler, okay, or you change the semantics of your code, or you keep the code semantics the same, which means you can hold locks for arbitrary periods of time, but then failure detection, failure recovery is harder, because you've got to pick from one of these two. Okay. So that's essentially, so that's why it says detecting token loss is non-trivial in the arbitrary case. Okay, so it covered several different algorithms. That's a table that actually compares them. Okay, you will see the message overhead is arbitrarily different. So you have centralized is 3, decentralized is 3 MK. We will not go into the details. We didn't talk too much about that. Distributed one is 2 times n minus 1. Here it's the number of nodes in the ring. Okay, that's essentially a message overhead. There's different delays. There are essentially 2 messages to get the token here. There are 2m because there's voting happening. There's 2n minus 1. Again, this depends on how many nodes there are. Okay? And then there are problems in each case. Okay? There's coordinator crash, starvation. There's n points of failure. Here, how do you detect a lost token regenerated and so on. Okay? So the short answer is distributed synchronization is a lot more complicated. And it gets complicated because of the failure issues. Because once you go down with holding the lock, or if there's a coordinator, it goes down, then there are all sorts of problems you have to deal with. Okay? There are no good answers, shouldn't say no good answers, no right answers on how to address the failures. You have to make some assumptions and then use those assumptions to deal with failures. Okay? Any questions on this? All right. So we are almost out of time. We'll stop here, continue from here next time.